So hello to everyone who's watching on YouTube. Since no one joined the session in person yet, I can please wait for like 5 or 10 minutes. That a will join the session. It's asking. So I guess since no one has joined the session in person yet, maybe I'll just get started so that yeah, while it's it. So yeah, if someone has joined person yet, I'll just get started and for the people who are working on. So first of all, maybe just to introduce myself. So hello everyone. This is the problem solving TA for NPTEL Social Network Analysis course for the Monday 6:15 session. Due to some reasons like we are having this time on Tuesday, but probably the session from next week on. So Monday 6 to 8 only. So this will be, I guess, our fifth session, and in this session we'll be discussing problems related to local community testing. This was discussed in this week's lecture. So once again, like previous weeks, this week also I prepared a bunch of like some lecture summary notes, which we'll discuss first, like that we have an idea of what are things to discuss in the lectures, and then we'll get discussing specific like problem statements or specific which will help you with solving the quiz question. So yeah, without further ado, I'll just get started. So maybe I'll go share my screen and so so I think now okay. So this week, like as I said, so this week we discuss what are communities, like different kinds of things. So like we have those and most of the three lectures were again based on like community detection and again like as is the norm, as has become the norm in like this course, like we have a bunch of definitions which we'll have to first go through. So there are a bunch of definitions and yeah, some are more mathematically involved than others, but yeah, more or less once you're clear with uh, all of these definitions and your intuitions, then like problems I believe are not so hard to solve. So yeah, we can get started with discussing about the lecture first. Okay, so what are communities? So what are communities in a network? So community detection, first of all, is an ill-defined problem. Like, what exactly is a community in a network? So, usually, how do you define community uh, in a more like informal setting? A community is nothing but a bunch of people who are like similar to each other. So, maybe in real world society, you can say like, yeah, communities can be maybe people belonging to like same religion or maybe people residing in the same area, or there can be a bunch of definitions about what exactly constitutes the community. Maybe a bunch of people who like the same sport or something like this, or who are fans of the same team. And yeah, so community detection by definition is an ill-defined problem because what we mean by a community is not mathematically concrete. So right now we are just giving like heuristically like okay maybe if some people like this thing then they form a community. If some people like other things then they form a community and so on. So there is not really a ground truth as to what exactly is a community. So there is no standard measure to assess like what thing is a community in or what thing is not a community. Uh, so we'll have to have like different kinds of approaches for uh, different kinds of problems. Like so, like there will be a bunch of definitions, and like each definition for a community is relevant in its own right. Maybe like there exist some settings where you will need like definitions of some kind. In some other settings, you will need definitions of some other kind while identifying communities. And note that we won't be doing like since we are doing this in social network analysis course, we'll be focusing on graphs only. So suppose we are given a graph, and then each node represents some person in the population, and then what do we mean by community? Communities are like a bunch of sets of nodes. So if you divide the graph into like some subsets of vertices, and yeah, these vertices, if they are similar to each other in some manner, then we'll say that those vertices form a community. And again, like there can be various kinds of definitions for communities, and so there can be diverse approaches to the problem. So yeah, so maybe we'll just maybe like first go through what kinds of communities are there, and yeah, discuss some of the uh, diverse, some of the actual approaches or some of the actual definitions which are used in different contexts for community. So, uh, in what are the types of communities? So there is something called disjoint communities. So, and which are also referred to as flat communities. And what happens in these disjoint communities is that uh, each node can belong to at most one community, and if yeah, so nodes and these are different functions. So basically, what are disjoint communities? So if you divide the set of vertices into disjoint subsets, so note that no two subsets have any vertex in common, then these are called like disjoint communities. Note that there can be some vertices which do not belong to any subset also, and that's also fine because it says that each node can belong to at most one community. So each node will belong to either one or zero. So there can be nodes which don't belong to any community, or in that case, you can say that the node forms its own community, so something like that. And note that these are not exactly like disconnected components. Like, so what can be one definition of a community? You can say that, oh, in a graph, like any two vertices lying in the same connected component are part of the same community. And that's maybe one kind of definition for a community. And that will be an example of a disjoint community. But note that there can be various other definitions. Like here, if you see this graph is a connected graph, but these are the blue vertices which have formed one community, green vertices form another, red the third community, and black vertices the fourth community. So nodes in two different communities can still have connecting edges, and yeah. So here you see that nodes in different communities can still have connecting edges. So it's not exactly like each community corresponds to just disconnected components. And these inter-community vertices, inter-community edges, are also called bridges in this scenario. Like, although we have like discussed the definitions of bridges in different contexts previously, using betweenness and stuff like that, but in context of communities, these inter-community edges are referred to as bridges. So yeah, so this is what disjoint community, and then there are like other communities also which are like overlapping communities. So again, if you divide the set of vertices into multiple subsets, such that members can belong to more than one community at a time. And so these disjoint communities can even share edges, and yeah. So these are also like prevalent in social, like these are also prevalent in social networks. So suppose, I think this example was given in the lectures also. So like, suppose we are forming communities based on like fan following, like uh, what what celebrity or what sports player does a person like. Suppose the population, and say, let's say like green vertices are the people who like Sachin Tendulkar. Similarly, let's say blue vertices are the people who like Virat Kohli. So there can be uh, some people who are fans of both the players. Like this node here is a fan of Sachin Tendulkar as well as Virat Kohli, and this is perfectly fine. Yeah. So this is what is called disjoint community. Okay. And then there's a third kind of community that called hierarchical communities. So, so you can think of hierarchical communities as like forming some kind of an hierarchy. And what so what do we mean by they're formed by some kind of hierarchy? So maybe like let's say initially we start out with some flat communities, and then we merge some components of flat communities together and form like a like bigger communities, which are also flats in themselves. So as you can see, like this is kind of an hierarchy that these kinds of yellow vertices will first belong to this level. At like the most granular level, these vertices belong to this kind of a community. But at maybe second level, all these vertices belong to this uh, dashed community. And yeah, and like similarly here, like these vertices belong to the small community, then they belong to this community, and then they have to belong to this larger community. So what's essentially going on is these hierarchical communities are uh, kind of an outcome of merging two or more flat or overlapping communities in network. So initially, if you like the initial community which you start out with need not always be flat, like it can be overlapping also, but these communities kind of form an hierarchical structure. So like as like hierarchies present in real world also, like in organizations, suppose you are drawing a node for like employees in an organization, then maybe uh, all these red dots form a certain team in an organization. So all of these have the same manager, but then all of these teams come together and maybe they all have the like same uh, uh, maybe same VP under which they are all working, or maybe like there's some senior even to manager under which all of these are working. So yeah, so this can be a higher community, and maybe like you can have a even bigger community which says like all these people belong to the same community, same they are working in the same organization. So something like that. Okay, so uh, I hope. Yeah, so yeah. So these can be linked to other hierarchical overlapping of flat communities. And yes, an example of hierarchical communities given is as discussed in lectures is like maybe various city level communities merged to form a state level community. So these hierarchical communities are also kind of uh, very interesting and kind of important. Okay. And then there are like some other communities which are local communities. Okay, and I think uh, as you may have also gone through lectures, so the techniques which we'll be discussing are mostly about local community detection. So these the four kind of communities, the local communities. So what are local communities? Local communities just show community structure from local perspective without focusing on global structure. So maybe like okay, so suppose you have a billion nodes in network, then maybe you cannot look at a graph as a whole. Like in real world network, like since networks can be very large in size, let's say billion in size. So in that case, I thought it is able to look at the whole graph at a single point of time. So like as you can see, like in these hierarchies, the overlapping or disjoint communities, and these are defined based on like maybe some metrics. These can possibly define based on some metrics which are for which one person has to see the whole graph at a single time and then divide these into communities. But note that we can't really afford looking at the whole graph if the network size is let's say 1 billion. And at that point of time, the best maybe what we can do is for each vertex, just look at all its neighbors around itself, around the vertex. Like maybe up to some extent, just look at like each vertex locally and some neighbors around it. And um, these are what are called local communities, which are just formed by maybe looking at a vertex and some neighbors around that vertex. And these are kind of the most important in like social networks because social networks are very large in size. So uh, usually local communities are the ones which are computationally the most tractable for us. So yeah. So these are local communities, and then like there will be algorithms which are related to like local community detection and so on. Yeah, we'll come to this later. And then obviously one really important aspect of social network analysis is maybe like, okay, if there exists some kind of communities, whether they will be local communities, hierarchical, disjoint, or maybe uh, overlapping communities, we kind of need to identify. Given any graph, we may be, we it would be good for us if we can identify if two nodes belong to if two nodes in the graph belong to the same community or not. And this helps us identify like if two people are similar in some sense or something like that, and that's like really important in like social network analysis. So there are various methods for community detection. Some of most of these I believe will be discussed in maybe upcoming lectures in the next week, or like a couple of them maybe we'll be discussing today also. So there are many community detection methods, like there are a method which can find disjoint communities present. There are some methods which can find overlapping communities. And lastly, there will be some algorithms which will help us identify local communities. And maybe like not this time, but in some upcoming lectures, we'll look at some of these local community detection algorithms, which will be most important. We also will be discussing algorithms which are quite important, but yeah, uh, some will be like even like, but maybe like not all of them are always used in real world networks. Some of them are, but not all of them. But the local community ones are almost used a lot, almost always used a lot. So, yeah. And then, okay, so now let's just come to like what different kinds of community like methods. So there are various kinds of community detection methods. So maybe first method is node centric community detection. If you like want to identify, so uh, if you want to just look at nodes and like want to classify the network in some kind of communities, so maybe one method is just finding clicks in a network, in the network. What's a click? A click is a subgraph uh, in which edges are present between all the pairs of vertices. As you can see, so this is in this kind of a graph, there is one click. So these are like with seven vertices, all of which have edges to each other. Similarly, there are these five vertices, all of which have edges to each other. So this is one click, this is another click. So maybe you can say that this click one forms one community, this click two forms second community. And yeah, these are like bridge edges between communities. So what's a click? A click is a subgraph, is a click if every vertex pair in the subgraph are adjacent. Just like every pair of vertices has an edge between them. That's what we call a click. And a click always has a diameter of 1. Why? Because for what's the diameter? Diameter is like the maximum distance between any pair in the graph. And note that uh, here in a click, like since all the pairs of vertices are adjacent, so if you pick any pair of vertices in a click, like they'll always have a distance of 1 since they have an edge between. So yeah. So clicks can be thought of as communities, but then again, like maybe this is uh, one way of thinking about like uh, how communities are formed. But there are a bit computational problems with identifying clicks in a network. Like uh, so the problem of finding clicks from a network is actually an NP-complete problem. Suppose you are given a network and I tell you like please give me all the clicks in the network so that I can refer to them as quantities. This is an NP-complete problem. So as of now, like there is no efficient polytime algorithm for this. So yeah, and these constraints on clicks are too strict a requirement because what's the constraint on a click? Like every pair of vertices should have an edge, and usually large leaks are not present in social networks. So usually you won't see that uh, a very large, you won't see a very large size leak in a real world network. And so maybe like this is not the best definition. Like this is not the best way to go about finding to classify things as common. But note that this is one of the most bigger problems for us that uh, finding places isn't the complete problem. But note that there is a third problem which is like large leaks are not present in social networks usually. And like these two things are kind of interrelated. So maybe like okay, like finding clicks from a network is NP complete, but what about finding clicks of small size? Like since large clicks are anyways not present in social networks, so maybe the cases where this problem uh, is NP complete don't really arise in real world social networks. Like even if it arises, then there is like a kind of a band-aid fix for this, and which is like what we call as K click. So K clicks uh, uh, is something uh, which kind of helps us overcome this problem of like the problem of finding clicks being NP complete and large clicks being not being present in social network. So what's a K click? A K click is a maximal subset of vertices such that for any two nodes, the shortest distance between them is less than or equal to K. So note that here we said that uh, we call a subset of vertices as click if the distance between any pair of vertices in that subgraph was actually 1. But in K-click, what we'll say is maybe a subset of vertices, a maximal subset of vertices, such that for any pair of nodes, the distance between them is less than equal to K. So a clay kick is nothing but maybe a subset of vertices such that the diameter is less than equal to K for that subset of vertices. So if the distance was 1, then one click is just the normal click. And note that in this example, like this set of vertices, 1, 2, 3, 5, 6, it's actually a 2 click. Why? Because you take any pair of vertices, the distance between the two vertices in this graph G is just 2. You just take these two vertices, 3 and 5, or maybe let's just take these vertices 2 and 6, then the shortest distance in them is 1. Similarly, between the vertices 2 and okay, between the vertices 2 and 5, the shortest distance is 2. It was 2 to 6 and 6 to 5. And similarly, the shortest distance between the pair of vertices 3 and 5 also is 2. And the shortest path is maybe from 3 to 4 and 4 to 5. So note that, yeah. So, uh, like in this example, actually, you can see that there is some kind of a so even while defining K clicks, like there is some kind of issues with definition of K clicks also, which was like present in this example. And what one of the biggest issues in K click is that okay, like we have defined that shortest path between any pair of vertices should be less than equal to 2 here in a 2 click. But note that like the shortest path need not always go through this subset of vertices only, which we have defined as the 2 click. Like a node not present in K-click can contribute in formation of shortest distance. For example, here, like if you just saw this subset, then between these vertices 3 and 5, the shortest path was actually from 3 to 4 and 4 to 5. But this 4 actually did not belong to uh, our 2 click. So there can be vertices which are which lie on like the shortest path, but are actually not part of the click. And that's kind of an issue for us. We would like the things to be like we would like things in a community to be self-contained rather than like taking use of some words which are not part of the community. Okay. So and usually two clicks are also known as friend of a friend in social network analysis because like two clicks are essentially nodes which are like distance two apart. So like if distance one node is a friend, then like the distance two node will be just friend of. So yeah, that's really we see that's some terminology here. Okay, so as you see, like maybe this is kind of an issue for us, as I already said that a node not present in cake we can contribute to formation of shortest distance. So what's the next natural definition? Which one can talk about for community detection? Like which can maybe solve this problem? So it's obviously so we can make the definition of cake a bit stricter and call it a K clan. And what's the K clan? Again, the shortest distance between any pair of vertices, like it's a maximum subset of vertices such that the shortest distance between any pair of vertices is like less than equal to k. But note that now we'll not be looking at the shortest distance between the vertices in the whole graph G. But what we'll be saying is that only the graph present in the set under inspection, only the nodes you present in the set under inspection are used to create the subgraph. So like in this given network, okay. Uh, so in this given network, maybe we'll talk about this. So even though this is a K click because the distance between 3 and 5 is like also 2. It's a 2 click, but note that it's not a like a 2 plan because the shortest path between 3 and 5 uses a vertex which is not the part of this subset. So this is not a 2 plan. So yeah. So if you have to define like if you just have to use the word if we define this kind of a set and you just have to use the word the graph itself. So it's a set itself. So only 1, 2, 3, 5, and 6 words are present. So using this subgraph, what's the shortest part, what's the diameter of the component, then like maybe the biggest shortest part PS5, which will take that from PS, which will which will which will got which got in the diameter of uh, component. And so that's why like see. So this will be actually a 2 click, but a 3 click. This subset of the 3 click for 7. This side and like the next of even if it's require like from the 2 click, but number 2. Here is this like 3, 3, 4, 5, 6 equal to feel like as you do for any kind of a pair. Okay. So the only difference between the destination state, so the mathematical conditions of the same state you can take that. The only difference is like while determining your shortest path, then take you take the whole graph, whereas in the plan you just take that set of vertices present in the set itself. Yeah. Then again, to the definition you need. So um, yeah, which is again maybe a extension of a plan, like and so like the maximum. So like here in the case plan, like we had all the functional case, like it's just some additional property about shortest path right effect. And like so cake and cake plan both has this maximality, like the subset should be of largest biggest subset. There should be no but like outside this word which you can have into the subset like this. And if you remove this condition, then it's all K club is a K class minus the map class. So we are like to be like this. Then subset of four. Then this subset of words is actually uh, is not a K class because like it's not a two class, and this is because uh, for this pair of vertices, like maybe the shortest distance is two when you use these vertices. But note that it's not the maximal success. Like if you add 54 this uh, uh, vertex, let's say six, then this 6 2 3 4 maybe it is, yeah. Why is it not maximal? Because with two the 64 thing, you add this set of vertices from a 5, then this whole set again becomes bigger. So that's why like this 2 3 4, this subset of a key is not like the maximal. I know that sometimes identifying maximality can be computationally an issue for us, and that's why we would like to do away with maximality, and that's where like this second case comes from. So even though this is not a two plan because it's not maximal, so, but it is a two club. So two club and so K club and K clan are same, identical definitions except that K club you just don't need one. 2 3 4 is not a K, neither a K, it's not neither a K click nor a K plan, but it is a because okay, so till now like we have started with uh, what can be possibly a good idea for countries, what we call click, and we just try to extend generalize that click on it, that happening. But still, like these type of things, uh, I am and all of these things are still computationally expensive for large values. So, like suppose we have to identify like 1,000 plus, if there are 1,000 plus, but, yeah, then you would have to look at the subset of vertices and see whether this person have like all pairs with this set of vertices have like different limits of 1,000 or so on, and stuff like that. And then sometimes also computationally. Yeah. And what's the appropriate value of K? I think like even though like some algorithm like at least the K club algorithm is not like maybe the K clan and the K click algorithms are actually much more completely expensive. But K club I think is not that much completely expensive. But this part is like one of the biggest. Like what is the value of K which is while um, doing this conversion? Like what is the right? Like maybe this case, like for some networks like this case will be something different. For some other networks, this case will be other value. And like yeah, so in some networks maybe 1K would gives a good community like federation. For some other network, some other K. So this task of deciding the appropriate K is actually and like something which is quite protected. So all of these kind of things are good starting points like cake and cake and so on. But maybe like that's not the most. So, okay. So then uh, there's another uh, criteria which is called K-flex, and I think similar thing has previously been discussed in the lectures as well, like not with the name K-flex, but I think in some other context. But yeah, so a subset of words in a graph is a K-flex, if every vertex of the induced subgraph G of S has degree at least S minus, and it's the like the K plus is a measure which is based on degree of. So a subset of vertices in a graph is a K-plex if every vertex of the induced subgraph G of S has degree at least uh, size of S minus K. So for example, in this GC, the word is 3, 4, 5, 6. So this 3, 4, 5, 6. So if you see the vertices, so like quite a very defining kind of a like K-plex instead of like K-click. So in K-click, we know that like if there is a K-click present, then what degree of all the nodes is something like for a subset S, if we do the click, then degree of all the vertices will be just the size of S minus 1. So now maybe we are trying to do some kind of a relaxation for a click. So previously we did a relaxation in terms of like distances, like we did K click and so on. But another relaxation for a click can be like relaxing the degree requirement for like for subset as a what in a graph. Like in a click, like the degree of every node will be S minus 1. But for it to be a case, if we just say that the degree of every node should be at least size of S minus, not size of S minus 1, but the case after the picture. So a subset of vertices is actually a click if it is a one plex. So one plex is just the regular, as an example here. So like subset of 5, 6, you see that every node has like 3 and size of 4. So like it is a one plex, but as you can see, for 4. Similarly, let's just look at this. So the 1, 3, 4, 5, 6. So 1, 3, 4, 5, 6. So these are like 5 and degree of so the minimum degree in this network is like degree 2 because it's 1 because it is induced a graph like this one has the 2 edges and 4. So 5, 6. So in this induced graph, we actually have this has a degree of 2 and yeah, so and the subset size is like 5. So 5 minus 2 will be a kind of 3. So actually this is a 3 plane. 3, 4, 5, 6. This should be the 3 plane. And like, but inside if you just look like 1, 3, 4, 6, so if you did not look the 5, so if you just look like the network as 1, 3, 4, 6, then like there are 4 vertices present and like minimum degree 2. So then this should be unclear. So the subset of vertices 1, 3, 4, 6 is a 2 set, but this 1, 3, 4, 5, 6 is actually is the correct. And then so there can be uh, another kind of definition for it. Like if we want to do away with the kind of like if you want to do away with maybe like this kind of set-based definition, so then there's another thing called K-core, which is again a degree-centric measure, and yeah, and a subgraph G prime of a graph G in which each node has degree greater than or equal to K is called a 3-core, or is called a K-core. And how do we form these kinds of cores? So a K plus 1 core subgraph can be created from the current K core subgraph by recursively removing nodes of degree K. So I think this kind of algorithm was uh,
discussed in the lectures, also like in some other context. So like suppose you are given a subset of vertices and you want to find out like if it is a k core, what's the value of k. So how do you do this? So suppose this is the subset of vertices which are given to us, and this is like the subgraph form corresponding to these vertices. Then maybe like at first level you just remove the degree 1 vertices, and you keep removing the degree 1 vertices till you cannot find another degree 1 vertex in the network. Like here you can see this blue vertex like has a degree 1. So if you remove this, then this vertex initially it had degree 2, but after removing this vertex, it also has a degree of 1. So you remove this vertex also. So both of these get added to level 1. Similarly, this vertex gets added to level 1, this vertex gets added to level 1. And now after deletion these two vertices, this vertex also has degree 1. So this also gets removed and gets added to level 1. Similarly, these two vertices also get added to level 1, and this also is level 1. So all these blue vertices form like one core. And then in the second level, what you do is you remove these green vertices which are like having degree 2. And after that, like you're left with vertices which all have degree 3. And so these form like 3 cores. So note that initially the degree might be, so for these vertices, initially the degree might be more than 1. Like even though they belong to one core, their degree might be more than 1. But after removing some of the 1 degree vertices, these also have 1 degree 1. And that's why they belong to one core itself. So yeah. So this is how you define K core. And again, the issues in defining like these k core and k plex is like finding these maximal k core or k plex is like an NP complete problem. Even though it's easy to identify whether a given network is k core or k plex, but in a bigger graph, if you have to find a small set of vertices which form like a k core or k plex, then this problem is NP complete. So again, maybe this is not really like it may be useful in some context, but not a really good generic measure for us. But important nonetheless because it's a good starting point for us on like getting started with communities and what are communities. Okay, so then maybe like we can move on to some other interesting definitions. And for this, first we started with defining uh, what is a cut. Like, okay, so now maybe we are moving away from these K core, K plexes, K clicks, and so on, and defining some other kinds of uh, definitions which will probably help us in identifying communities a bit better. So, uh, so what is a cut? A cut is a partition of vertices of a graph into two disjoint sets. And what's the like intuition behind like defining things with respect to a cut? So most interactions uh, like if there are communities, then most interactions are within communities, and interactions between communities are few in real world network. Like this is the definition of communities, right? Like people interact within a community more than they out than what they interact outside, and this can be captured by most like most interactions being within communities and interactions between like communities to be few, and this corresponds to like in some informal sense, like this corresponds to like minimum cut problem. Because what's a minimum cut problem? We have to find a graph partition such that number of edges between two sets is minimized. So a cut is a partition of vertices into two disjoint sets. And let's say like these two disjoint sets correspond to two communities in which we are dividing the graph. And now since we want like interactions between communities to be as few as possible, so we want like the edges between the edges going between these two disjoint sets to be minimum. And this is just precisely the minimum cut problem, that finding a graph partition such that the number of edges between the two sets is minimized. So like yeah, so this intuitively corresponds to like minimizing the interactions between communities. And so like this can be a good starting point for us for community detection. But note that there is again a bit of a problem here. So like as you can see in this network, uh, suppose we are starting with dividing the graph into like maybe two communities, then the minimum size cut actually is from this vertex 9 to 7. And so the two communities formed, if we just take things into account using the minimum cut, will be like, so this 9 vertex will form one community, and all these other vertices will form another community, which is maybe like not really a good community breakdown, at least for this graph, because like maybe like uh, making this whole subset as one community and this whole subset as one community, it is like I have no mathematical like foundations for saying this, but this and this distribution looks more like a community than this and this. So yeah, so maybe like minimum cut is not a really a that good of an idea. But like what's the issue here? So this so even though cut size is small, but these communities are quite unbalanced in size, and this is what is causing us problems. So maybe we should one thing which one we can try is like kind of taking the sizes of these communities also into account. Like so, trying to find maybe some kind of balanced communities, like communities which are of balanced sizes, while minimizing the cost of the cut. So that kind of a measure, and this is where these normalized cuts and ratio cuts come into the picture. So we'll stick to the like intuition of cuts that we need to minimize the edges between communities as much as possible, but we also need to kind of take into account the size of the communities. So yeah, so minimum cut returns an imbalanced partition with one set being a singleton. So if we just change the objective to consider community sizes also, and what this means is like so instead of taking the value of just like cut like instead of just taking the number of edges between ci and ci bar into account, we also take into account the size of the set ci. And yeah, so now we try to kind of minimize this kind of a value. Then this is what is called like a ratio cut. So suppose we are dividing so suppose we are dividing a graph into some small k number of subset, like, and we want to call these as communities. Then how do you define like a mathematical metric to measure the quality of this community in this ratio cut setting? So we just say it's 1 over k summation I equal to 1 to k, the size of cut from like ci to ci bar. So maybe like maybe just the number of outgoing edges from this partition ci and divided by the size of ci. So this is what is called ratio cut. Another definition can be like, so this is different from ratio cut, which is what you call normalized cut. So here you don't divide by the number of uh, vertices in the partition, but rather by the volume of the partition. And what do you mean by volume? So volume is just like sum of degrees in Ci. So yeah, if you take the vertices of Ci into account and just sum of their degrees, then that's what is called volume of Ci. So in normalized cuts, you take the size of the cut divide by volume of the cut, and ratio cut you take like size of the cut divide by uh, number of vertices in the cut. So yeah, so these are two measures like which now like so we are now getting into so first started with maybe some measures which are computationally bad or like will not make much sense, but these measures are something like which kind of prove to be somewhat useful in real world. So even though finding like ratio cuts and anomaly cuts are NP complete problems, but there exists some kind of like approximations for these which make our life a bit easier. So yeah, so maybe let's just do a method. So this example was covered in lectures, but maybe we'll just start with this again. So maybe let's just see like okay, like if I had to just divide the graph into like two communities, then what I said was like dividing this as 9 and this whole as one thing was maybe not a good community, but like this the vertex is separated by this green line, like this green cut, as kind of a better representative for communities. At least visually it looks to us, and let's mathematically verify also whether like our definitions of ratio cuts and normalized cuts actually correspond to this. So let's just see like uh, for this red cuts partition, which is like vertex 9 on one side and like all of these vertices on the other side. So what will be the value of the ratio cut? So the formula was like 1 over k. So note that here k is just 2 because we have found two communities. So it will be 1 over 2. And then like the size of the cut C1. So size is like the number of outgoing edges out of this set, which consists of just the vertex 9. So there is just one uh, edge outgoing. So it will be 1 divided by size of this set of the cut, size of the set of number of vertices, or maybe like number of vertices in the cut, which is just 1. So this will be 1 by 1 plus. Now we see for the second set or the second community which we define with respect to this cut. And for this also like this set the number of outgoing edges is 1 because this is the only outgoing edge. So numerator will be 1 and there will be 1, 2, 3, 4, 5, 6, 7, 8, 8 vertices. So denominator will be 8. So it will be half times 1 by 1 plus 1 by 8. So for this, the ratio cuts value for this red partition is somewhat like 0.56. And what's the normalized cut value? So normalized cut value is again like 1 by k is 2, so 1 over half, 1 over 2, and then like numerator is 1. So because the cut going across is like 1 divided by volume of the cut, and volume is just like sum of degrees. So for vertex 9, like the sum of degrees is just 1 because it has just the degree 1, so denominator will be 1, and plus this one will again correspond to like this outgoing edge divided by summation of degrees in this subset of vertices. So this 7 has a degree of 3, this 8 has a degree of 3, so 3 plus 3 plus 4 plus 4, so this will be 14 plus 4 18 plus 3 21 plus 3 24 plus 2 26. Okay, maybe I miss something? Oh yeah. So for the 7 I counted as 3, but it is actually 4. So yeah. So the sum of degrees of vertices for this set will be actually 27. So you have like 27 in the denominator and 1 in the numerator. So it will be like 0.52, the normalized cut value. So so these are even though different metrics, like ratio cut gives 0.56 and normalized cut gives 0.52 for this red cut. And similarly, like similar calculations when done on like green cut. So if you take like this as one partition and this as other partition, it actually comes out that the ratio cuts value is 0.45, which is actually lesser than uh, the ratio cut for this red cut. So like and similarly like the normalized cut value is also like lesser for this green cut than this red cut. So what this kind of shows us is maybe like this ratio cut and normalized cut are better measures as they actually give us this green cut instead of this red cut. So final value. So and this is what this claims that ratio cut and normalized cut kind of always prefer some balanced partitions, like partitions which are of similar sizes, rather than very skewed or unbalanced partitions. So yeah, I hope this makes sense. But like I believe calculating the values of ratio cuts and normalized cuts is kind of an important exercise and may get asked up like in exams or something. So yeah, this is kind of important for us. Yeah. So now maybe we can move on to uh, like some next definitions. Okay, maybe I'll just mute myself for a second, guys, and yeah, I'll come to the next definition in a couple of minutes. Sorry for this. Sorry for the yeah. So yeah. So now yeah. So this is one measure which is kind of a good measure for us. Like at least ratio cuts and normalized cuts are good measures. But again, like as you already said, like maybe there is this like not one glove fits all. So maybe there are some other measures also which are also good for us. So then there is this measure which comes into the picture, which is called like edge betweenness. And I think this edge betweenness has already been like discussed on numerous occasions in previous lectures. And like, what's the edge betweenness for an edge? It's just like uh, the number of shortest paths that pass along that use actually that edge. Like, so you for every pair of vertices, you take into account the total. Uh, so the fraction, like, so what's an edge betweenness? So the fraction of the fraction of number of shortest paths which actually use that edge is what's like edge betweenness for an edge. So for example, like for any edge, if you have to find out the edge betweenness, then what you just do is like take any pair of vertices, like some overall pair of vertices, and what you do is like take any pair of vertices, then just take like then just find the total number of shortest paths between that vertices and like the number of shortest paths which actually use that edge. And this ratio, when summed over all the vertices, all pairs of vertices, gives you the edge betweenness. So for example, maybe just to refresh it for you guys. So like so for this edge 1 comma 2, so what's the edge betweenness for this edge 1 comma 2? So so if we have to look at like all pairs, so let's just look at the pair 1 comma 2 itself. So if the pair of vertices is 1 comma 2, then there is only one shortest path and it uses that edge. So it will be like 1 divided by 1. This value will contribute from this pair 1 comma 2. And then if you look at the pair of vertices, maybe let's see, like mm, so maybe yeah. So this pair of vertices like 2 comma 5. So this pair of vertices, this 2 comma 5, uh, actually uses this 2 comma like so the shortest path between 2 comma 5 will use like it can be like something like this, like the shortest path between like 2 comma 5 will be of length 3, 1 2 3, and one shortest path can be there which uses this edge like 2 1 2 1 4 2 4 5. So for similarly for like 2 comma 6 2 comma 7 2 comma 8 and 2 comma 9, so this 1 comma 2 edge will be used. And for all these six vertices, actually, like it will be used in exactly half number of paths. And why is this the case? Because like as maybe it's mentioned, like all shortest paths have to either pass through 2 1 or 2 3 to reach to any of these vertices. And so like and the numbers will be equal. So yeah, so each of these pairs like 2 comma 4 2 comma 5 2 comma 6 2 comma 7 2 comma 8 and 2 comma 9, each of these pairs contributes a value of half, and there are like six such pairs, so it will be 6 by 2. So the edge betweenness for this edge, so and this edge only occurs in these pairs. Like after in all of these vertices, you can verify this yourself. So in this graph, like 2 comma 1 appears in shortest path for only these pairs, and so like the edge betweenness for this edge is something like 4. 6 by 2 plus 1, which is 4. And the edges with higher betweenness tend to be the bridges between two communities. So usually what happens is like maybe so one good way to get started is maybe the edges which have higher betweenness value. So we'll try to have the edges with the highest betweenness values. We'll try to have the endpoints of those edges in different communities. So these kinds of edges can be thought of as bridges between two communities. Like if they are bridges, then like their endpoints lie in different communities. So yeah. usually, like, again, it's very intuitive argument. It's not a very mathematical, formally mathematical claim, but like intuitively, like if an edge like divides a large number of shortest paths, then maybe like it is a bridge between communities. And yeah, and so this like easily gives us then uh, one method to maybe another method to maybe uh, divide the graph into communities, and which is like clustering based on edge betweenness values. So initially there are some betweenness values in the graph, like you just compute for all edges the edge betweenness values, and then we just remove the word edge with the highest betweenness value. So here the like actually the edge 4 comma 5, let's just, so it will come out from these calculations that the edge 4 comma 5 in this graph has the highest betweenness value. So you will kind of remove this edge, and on removing this, actually the edge 4 comma 6 becomes the edge with the highest betweenness value. So this edge, uh, so you keep on removing these edges with highest betweenness values, and you will see that you will kind of start forming clusters. Like if this 4 comma 5 is removed, then this 4 comma 6 betweenness actually goes even higher, because now this becomes central to uh, shortest path between this part and this part. So then when these two edges get deleted, then one community is like 1, 2, 3, 4. The other community is like what is 5, 6, 7, 8, 9. And now if we have to further divide this into like further subcommunities, like suppose we want to divide it into 3 communities, then actually like this edge 7 comma 9 will have the highest betweenness value. And then if you remove this, then you will again obtain another community. So if you want 3 communities using clustering based on edge betweenness, the communities obtained will be 1, 2, 3, 4, 5, 6, 7, 8, and 9, which seem quite a nice decomposition, at least visually. And if you just had like constraint of you just want 2 communities, then maybe these 2 communities are the best fit. So this clustering based on edge betweenness is also a very nice method. So for now, like we have found like two methods which are like quite nice and like work really good, which are which are like these clustering based on edge betweenness and these ratio and normalized curves. But then there is another method like which I think was described in the lectures also as like maybe the most important uh, method in like community detection, and like it's almost used everywhere in social networks. Like although all of these like networks are also nice, like using edge betweenness and like these ratio cuts and normalized cuts. So like all of these actually have like use one drawback for all of these is that you need to use the whole graph information. So like you need to do computations based on like the whole graph, and like computation based on like taking into account like all the nodes of the graph. Like suppose there are a billion nodes, then that becomes kind of computationally very expensive. And so even though these are nice ideas like clustering based on betweenness and like ratio cuts and all, but they are somewhat computationally expensive. So if we even want to say some more computation while doing good on like maybe commodity clustering side, then uh, this method of like modularity comes into the picture, which is like a really nice research which was proposed in like early 2000s and late. And yeah, so as I discussed already, like node-centric methods discussed so far are not very useful when the network is large. Whereas now this modularity detection, it comes from the word module, and it determines the quality of a community structure. So actually, like if you are given some, let's say some structure, community structure, like you're given some division between communities, then like one metric which you define was maybe ratio cut or normalized cut. But this modularity, you can also define like how good a community is based on this metric, which is modularity. And like even though it's a metric, like people have it after you to find like good algorithms with good modularity also. But let's come to that later. But for now, let's just think of it as a metric, like how good a community structure is. So, and it's based on comparison between like actual number of edges in a subgraph and its expected number of edges. And expected number of edges is calculated in the null model. So all of this technical details will be coming to later. But right now, like so the high level idea of modularity is okay, like so why are communities forming? Like the simplest intuition for this modularity thing, maybe this was discussed in the lectures also, is that okay, like suppose you are given a completely random Erdo Sreni graph, like a completely random graph, you are given a completely random ER graph, then a completely random graph should not have any community structure, right? Like community structure arises because of non-randomness. Like people ask, like if everyone is just assigned like some characteristic at random, then you will expect like the least kind of community formation to be present in that kind of structure. And now, but in the actual real world network, there are some like bond formation or something which are like non-random phenomena which lead to these community formations. So maybe one way to think of like detecting communities is detecting how far is our actual network graph from a completely random graph. And this is precisely what modularity captures. Like it defines a metric which captures like how far is the actual real world network, uh, how far is it from like how much does it deviate from a completely random graph. So that's why like it counts actual number of edges present in a subgraph and the expected number of edges. Expected number of edges in a random subgraph. And expected number of edges is calculated by assuming a null model. And what do we mean by null model? So each vertex is randomly connected to other vertices. And like although like all the properties obviously need not be like completely uh, like arbitrary. Like some of the structural properties are preserved, and one of the most popular structural property which is preserved, the degree distribution. So suppose like in the real world network, like every node has some degree, right? But now we want to form a random net, like we want to say that how different it is from a random network. So we don't just take any arbitrary random network into account, but rather we take the random networks which have like the same degree distribution. Like we take into account all the networks which have like the same degree as our real world network and choose one of those networks randomly. Yeah. And this is what we call the null model. And like I hope like this intuition makes it a bit clear, like how far is the graph from a random graph which follows the same degree distribution is kind of what gives us a really nice idea of like what kind of community formation may be at work here. So maybe let's not get into the mathematics of like what's how it like. So there's this easy formula for like determining. So suppose we are given a community structure. So we are not talking about algorithm to find a good community, but like it can also be done. Like just trust me. And as it was in the lectures also, like people have adapted this to algorithmic structure also, and maybe we'll see this in the upcoming lectures also. But for now, like suppose you're given like some community structure and you want to detect how good is the community structure. Like in the ratio cut or normalized cut also, we just define some kinds of metric as to find out like how good your community structure is. So here like this modularity is also a metric, and for a given community structure, the value of modularity is given by this value, which is like 1 divided by twice the number of edges, summation over aij, where ai and j are like pairs of vertices in a graph, and this small aij uh, and like minus like degree of I times degree of j divided by twice the number of edges, and like this summation multiplied by delta of community of I comma community of j. And like so this term might seem a bit mathematical in nature, but like what it's just saying is like not really like too hard. Like all of its derivation was also discussed in the lectures, but maybe you can see the lectures videos for the derivation. But like I'll just stick to describe this mathematical formula. So what it's just saying is like so this is like 1/2 divided by number of edges, and then you sum up over all pairs of vertices. This aij value, this aij is one if there is an edge between I and j present in the real network, and zero otherwise, and minus degree of I divided into degree of j divided by 2 times the number of edges, and then you multiply this term by del of community of I community of j. And what does this mean? Like this del term, like even though this looks mathematically quite big, this delta term, what the saying is that whether the pair I and j belong to the same community or not. So if I and j belong to the same community, then this term is 1 and it is 0 otherwise. So this term is either 1 or 0. Then degree of I, degree of j terms you already know. And this aij term is 1 if I and j have a common edge, otherwise 0. So this is like, even though this formula might look a bit daunting at first, but this is really a very simple form. Yeah. So I hope it's clear to everyone. And then like, again, it was discussed in the lectures that you can have like this formula, this can also be written in an alternate form. So there can be an alternate formulation for this formula, which is just mm, like this formula, the above formula like can be written as like, it's not a different definition, it's the same definition, but uh, like it can, like this thing can be derived from the previous formula and vice versa. And the other formulation for modularity is like yeah. So here, like earlier, you summed over all pairs of vertices, and that was called maybe like yeah, vertex formulation for modularity. This is like a community formulation for modularity. Here you are summing over all the communities, and what value are you summing over all the communities? So for so this is like mn divided by number of edges, where mn denotes the number of edges inside the community, and so so basically like the number of edges which are actually present inside the community, like both the endpoints of the edges are belong to the community mn or belong to the community n. So this term mn by divided by the total number of edges in the graph minus kn divided by 2 times number of edges whole square, where kn is just uh, summation of degrees uh, of all the vertices present inside the community. So summation with respect to like summation of degrees, where degree is with respect to like whole graph. So this mn term, like this mn term captures the number of edges present inside the community, and just kn by 2, this term captures like number of edges present inside the community, like summation of degrees of vertices inside the community will be like number of edges present inside the community as well as going across the community. Because this kn term has all the edges, like degrees of vertices, so all this. So some edges might belong to the community, some edges might belong not to the community. This kn term involves both of these things, whereas this mn term just involves like number of edges which belong inside a community. Yeah. So very fun. So this is like if you apply for any graph this formula for any community formulation or the other formula, this formula, the value of modularity will come up to be the same. And here are some examples for modularity in a graph, right? You can work this out yourself, like whether these values stack up or not. But like actually one thing you can see is like why like that is modularity actually good also. Like actually what comes out here like is uh so if you want like modularity to be as high as possible, because modularity is a measure of how far is a graph deviating from a random graph. So more is it deviating, it means like better is the community. So and it can be seen that like you can calculate yourself that if for this kind of a graph, if you form one community like this, the green community and the purple community like this, then the modularity comes out to be higher than maybe let's say if you form the graph like this, like you had this three vertices here as one part, these five vertices other as the second part. If you had this, then the community actually would be like then this modularity is a lower value than the optimal modularity value. So this is the worst of community according to modularity than this community. And visually also this makes more sense that
this partition is a much better partition. Okay. And why like modularity? So successful and useful is as you can see all the other ratio cuts and everything involved maybe a lot more computation, but uh, finding out value of modularity is just based on degrees value. Like what you just need to find out is like it just depends on like maybe the number of edges present inside the community and just the degree of node. So it's a very simple definition and like um, finding finding like community decompositions which have like high modularity values is also like computationally efficient. So yeah, so it's more local because it looks mostly at just the degrees of vertices instead of looking at the whole graph. Like in every term, you just have to look at degrees of vertices. So yeah, it's kind of a like, and that's why like modularity is kind of used a lot in like real world applications. So yeah, so if you if like, although I would recommend that because those cliques and everything started the mathematical foundations for the community detection and like what our understanding is today is because like someone started with all of those things first and then we slowly improved upon those things. But if there is one key takeaway from all of these lectures, like all of the things which we discussed today, like if I have to say what is the main key takeaway, then it has to be modularity. It's the single most important thing in community detection. So yeah, so please pay the most attention to this. So yeah, so okay then. So I guess since we have discussed so this was more or less what was covered in this week's lectures. So since we have covered all of this, then maybe we can get started with the questions. So I think the questions will be pretty simple since like we have already discussed quite a bit of theory behind all of this. So yeah, I don't think the questions will be quite difficult. I would have liked that some of you would have been present in person also so that you guys could answer the questions. But yeah, since no one is present in person, so yeah, and I can't really interact with the YouTube audience, so maybe I'll just quickly answer all of these. But most of these are quite simple questions once you understand all of the stuff which we discussed previously. Okay, so the first question says that Indian railway system with its 10K stations is grouped into 70 divisions, which are further grouped into 18 zones. Assuming a single station can only belong to one group, the following can be employed to present the system as a network community. So, what kind of a network community will be good for representing this railway system? So, note that a single station can only belong to one group. So, what we can have is uh, like a group of some stations together can form a zone. Like there are 18 zones, so these 18 zones uh, so okay, so there are 10K stations first of all, which are divided into these 70 divisions, and then these 70 divisions are grouped into 18 zones. So first you start off with these 10K stations, and then we know that these stations can only belong to one group as is given to us. So these 10K stations will be divided into these 70 divisions. So you can uh, form some subsets which will be actually disjoint, and yeah. So like these will be like, so since every station can belong to only one group, so you can have like a non-overlapping. So you will have non-overlapping subsets which will be so there will be 70 subsets, and all of those will be non-overlapping, and each subset will correspond to one division. And now these 70 divisions will be further grouped into 18 zones. So this means that now like you can have a hierarchy kind of structure. Like these 10K stations can be grouped into the 70 divisions, and now these 70 divisions will further be grouped into 18 zones. So it will be kind of a two-level hierarchy for us.
Like a station will belong to some division, and some division will belong to some zone. So yeah. So that's why this will be an example of a non-overlapping hierarchical community. So, so this will be like option B, as is clear from the definition. So yeah, so it's not really not difficult. And then second question is, what will be the edge centrality of any edge in a clique with a number of nodes? Okay, so this is an interesting question. This involves a bit of math. So what was edge centrality? It was the fraction of like shortest path in which that edge appears, right? So we will just do this. So consider any edge. Consider any edge. So like all the edges actually will have an identical edge centrality, because in a clique like all edges are kind of identical. And what will be the centrality? We'll just see. Consider any edge x comma y. Uh, then like in which shortest paths will this edge appear? This x comma y edge appear. So it can only appear in like, so because in a clique like between any pair of vertices, the shortest path is of size 1 only, of length 1 only. So here like the only way this edge can appear in the shortest path is when you are considering just the pair x comma y, and in no other pair will this edge appear as shortest path. So then the edge, then this edge appears in the shortest path between x and y only. This edge only appears in the shortest path between x and y. And yeah, it will be the only edge lying on shortest path between x and y. And so what does this mean? So what this means is that like the fraction of shortest paths uh, in which this edge appears for x comma y will be 1, and this fraction will be 0 for all other pairs. Thus, the fraction of paths, shortest path on which x comma y appears, on which the edge x comma y appears, is 1 for the pair x comma y, because for this pair like only this edge, taking this edge is the only shortest path, and 0 for the other pair. Why 0? Because for any other pair of vertices like this x comma y will never appear in the shortest path. So thus edge centrality for any edge is just equal to 1. Yeah, in a click is just equal to 1. So yeah, I hope this makes sense. And now we can move on to the next question then. So we can differentiate between disconnected components and disjoint community on the basis of following. So what's the difference between disconnected component and disjoint communities? So yeah, so as we discussed previously, like disjoint communities and disconnected components are actually different, because nodes in two different communities can still have connecting edges. and these are called bridges. Whereas disconnected components can never have bridges because they are by nature disconnected and so should have no edge between them. And so what this actually means is that yeah, so these bridges, so maybe yeah, so maybe these bridges are like what help us distinguish between disconnected components as well as disjoint communities, because disjoint communities will have bridges but disconnected components won't. So yeah, so option D, as disjoint communities will have bridges, whereas disconnected components won't. So yeah, this is why option D is correct. Okay, and now like based on this figure, I think we'll have to answer the questions 4 to 6. This is a graph given to us. And now the problem is if A, B, F is a K click, what is the maximum value of K? So let's say this A, B, F, this subset of nodes is a K click. Okay, maybe not the maximum, but yeah, what is the yeah. So if A, B, F is a K click, then what is the value of K? So uh like so if ABF is a K click, so let's just see maybe so what's the definition of K click? Every pair of vertices should have a distance less than equal to K. And now you can see that for the pair AB, the distance is actually less than equal to 1. Similarly, BF is also distance is 1. Similarly, AF is also 1. So what's the value of K? Here just K equals to 1. K equals to 1 as all pairs of vertices have a distance of 1 in the graph. So yeah, simple question. And the next problem is is the set B, E, and F. So this set B, E, and F, is this a K club or not? So this B, F, E. So this part, okay, maybe not a K, but yeah, I think we should be talking about maybe two club. We have to define some value of K, right? So again, what was the definition of a K club? So the K club was so so the K club was that uh, when you take the distance between using just these nodes, the distance should be less than equal to K. So here it's a two club. So between BF and E, the distance between any pair of vertices should be less than equal to 2. Then it will be a K club. And you actually have to, you don't need a maximality requirement in a K club. Like you need it in K clan, but you don't need it in a K club. Just as the revision, maybe we can see here also. So first start with K clicks, then instead K clan, which have maximality condition, but then we have K club, which don't have the maximality condition. So yeah, moving on to this. So yeah, so indeed it can be seen that uh, for any pair of node like between B and F, the shortest distance is 1, F and E shortest distance is 1, but between B and E, shortest distance is 2. So yeah, it is indeed a 2 club, because between B and E, you use the node F only, and you are talking about this B, F, E only. So yeah, so this is yes, as uh, clear from the definition of 2 club. So yeah, not really a too hard of a question, but more of a conceptual thing. And yeah, so then the problem states is there okay, so maybe I should have written this as yeah. So maybe I should in the three club because like if the problem was there are two club in the network, if so name it, then this BEF was anyways a two club. So there can be multiple like three clubs here. Like we have to just name one. So name at least one. Yeah. So is there a three club in the network? If so, name at least one. So it's like quite easy to see. Like you just have to form like any one and like yeah. So this B C D E will actually be a three club because like for this B C D E, like you can see for the pairs B and E, the shortest distance between these vertices is three. In actual graph, like the shortest distance might be two, but we have to consider only the vertices which are present in the subset. So these vertices actually form a three club because for any pair of vertices, the shortest distance is less than equal to three when you consider this graph. And like we don't need any maximality requirements here. So yeah, we don't need to check for that. So yeah. So yeah, there is a three club. Yes. Uh, B, C, D, E is a three club. Okay. Okay, so now we are in the seventh question. Like now we don't need the figure. So the seventh question says that the time complexity of finding the maximum size clique in a network with n nodes is. So what's the time complexity of finding the maximum size clique in a network with n nodes? So actually we discussed actually that the problem is NP hard. This was discussed. So like at least for now we don't know any polytime efficient algorithm for the problem. So it definitely cannot be order n squared, cannot be order n, it cannot be order n cube. It is actually like order n raised to power n. And why is this? Like how do you check if how do you find maximum size clique in a network? So one very basic algorithm can be maybe just look at all possible subsets and just check whether that subset forms a clique or not. And so like yeah, for so for all possible subsets of vertices, so like yeah, and that will be like an exponential time algorithm. Although I don't think we need like this n to the n, we can do it in 2 to the n or something. But yeah, you're just doing a bit overkill. But yeah, but like since like it's an NP complete problem, like anyways, like we have to select the best option out of all of these. So it cannot be like polynomial time because we don't know of any like if it was polynomial time, then we would know that p equal to np, but we don't know that yet. So it's actually like order n raised to power n here. So so the best option out of all of these is like order n raised to power n. Maybe like some better complexities exist, but out of all of these, like these three are definitely out of the picture. So this is the best option. Option C as max leak is NP hard and no known polytime algorithms. So option C is the most appropriate. And like order n raised to power n size algorithm is quite trivial. Like maybe it can be reduced to like 2 to the n. Just choose like any possible subset of size, like just for all possible subsets of vertices in the network, just check whether it is a clique or not. And yeah, that can be done like something like order n times 2 raised to the power n time. It can be done something like order n 2 raised to the power n time, and yeah, in that time you can find out solve the max leak. So yeah, but yeah, like for now, like since option does not have 2 to the n, but it has n to the n, then you can like just uh, mark this as correct instead. Okay, then the eighth question is any k click is also a k club. Is this statement true or false? So note that in a k click, we say that for any pair of vertices, the distance between them is less than equal to k. But in a k club, you need that the distance is less than equal to k, considering the vertices which are present inside the network. So as we discussed in one of the examples, like this part, this is actually a two click, this subset, because but it's not a like two club, because the shortest path between 3 to 5 is, if we have to take it as 2, then we have to take a vertex which lies outside this set, which is not permitted. So it's not a two club, but it's a two click. So any k click is not necessarily a k club, but the other side will be true. A k club will be a k click, but like the problem is this part. So false, as is clear from the definition and the example discussed in the lecture. Yeah. Okay then. Okay. So refer to the following figure for question not 9 and 10, but just maybe for question 9. Yeah. Yeah. So suppose we are given this. Suppose we are given this graph, and now we have to find out like in this given network, what is the one core subgraph for this network. So note that we define like how do you define core. So in a k core, like so if you have to find one core, what we do is like we just keep on removing the vertices of, okay, maybe, yeah, maybe I should not have options for this, otherwise it just causes more confusion. The figure, what is the one core subgraph? So yeah, so what will be a one core subgraph in this network? Yeah, actually, you can see that. So this vertex 1 has a degree of 2, so we cannot remove it yet. This vertex 5 has a degree 3, we cannot remove it yet. So in a one core subgraph, we just have to remove vertices of degree 1 first. So this 2 also has more degree, this 3 also has more degree, but this vertex 6 has a degree of 1. So this can be removed. So this will be belonging to the one core subgraph. And is there any other vertex, like after removing this vertex 6, that a degree of vertex 3 becomes actually 4. So it still cannot be part of like the one core subgraph. So note that only vertex 6 is the part of one core subgraph here. No other vertex is the part. So yeah. So just this is the final answer, because only vertex 6 has like degree 1, and after removing this, like none of these vertices are degree 1, so all of these will not be part of any one core subgraph. This is the answer. Okay, so okay then guys, I guess this was it what I had for today. So we just had 9 questions for today instead of 10. Okay. So yeah, so in today's session, we discussed about, just a recap, like what are communities and what are different kinds of communities, and then different community detection metrics and some methods for community detection. And the most important key takeaway was this modularity thing, which will be coming up in the future lectures also. And then we discussed some like quite simple questions, like at least based on the, which was just based on like what was discussed in the lectures and what we just revised today. So yeah, so if you paid attention to the all the summary and stuff, then like the questions would be a piece of cake. So yeah. Okay, so I guess this was it which I had from my side. So hopefully, so thanks for watching the session, guys. Whoever is watching on YouTube. So hopefully, I'll see you guys in person next week on on Monday, like 6 to 8 p.m. session. Like it's really much better if you guys attend the session in person, because then it gets a bit more interactive. So yeah. So hopefully, so I'll just maybe stop sharing, and yeah. So hopefully I'll see you guys in person next week. So till then, goodbye and thanks for watching.